All right, welcome students. Again, we're going to take a look at the realm of thermodynamics and kinetics. Today's video will mostly be focusing on kinetics. So quick review, we talked about thermodynamics the other day, and we said that that realm deals with answering kind of one question in chemistry, and that is, can a reaction occur? And we said in order to answer that question, we had to look at two separate areas, and one was enthalpy, or the heat of a reaction, or heat of formation, as it's referred to. And we looked at the formula that we use in order to calculate the enthalpy, or delta H, and what that tells us and what that communicates to us. And then also we have to look at the entropy of a reaction, and we're expecting that to obey the second law of thermodynamics, and that a system goes from, as something goes through a reaction, that system will go from a state of order to disorder. And so we were expecting an increase in disorder. So if we go through all of that and we discover that the reaction can occur, now we're going to enter the realm of kinetics. And we said that kinetics deals with a couple questions. And the first is, will a reaction occur? That's the first question. And then the second question is, at what rate will it occur? And today we're mostly going to deal with the first question, will a reaction occur, and kind of dealing with what are some possible barriers that are in the way of a reaction occurring. So if we've said, yes, it can occur, we've calculated our enthalpy and our entropy, and then combine those together to find our free energy of the equation. We find out that it has a negative delta G, and therefore it is a favorable reaction. It should be able to occur. The next question is, well, does it actually occur spontaneously or not? And so that we're going to kind of get into the realm of kinetics, and then we'll have part two of kinetics that will deal kind of with the rate, and that will be for another day. So let's first of all define what kinetics is. Kinetics is the study of the rates of reactions and the steps by which they occur. And so today we're actually going to kind of be looking mostly at the steps by which they occur, even though we will kind of discuss some more of that at a little bit later date as well. And actually, before we get to that, let me back up. In your notes, so it'd be a good idea if you had your note packet out with you, if you don't already, you'll see that there are some example reactions that I put there for you. And I already have the delta G calculated there for you. And these are just for examples, and you'll notice all of them are negative. So we would say that all three of these reactions there, the first one is the oxidation of a diamond, the next one is the burning of methane, and the last one is a neutralization of an acid and a base. And all of them are energetically favorable. In other words, there's an overall loss of free energy. But okay, as you look at them, I made a couple notes for you to look there. So in answering the question, can the reaction occur, our answer to all three of these would be yes. But if you'll notice, that doesn't necessarily, there's some things that seem to hinder some of these. Like the first one, the oxidation of a diamond, that reaction will occur on its own, but it occurs at a very slow pace. Matter of fact, a pace that would be basically invisible to the naked eye. So if I'm looking at that, I'm not going to see an instant reaction, even though I know the reaction should be able to happen. So that kind of deals with, well, okay, what about the rate at which it happens? And that falls into the realm of kinetics, and we'll talk about what are some factors that may either speed it up or slow it down. The second one there, the burning of methane, which we'll maybe play around a little bit, have some fun with in class. There, of the three example reactions that I gave you, that one is the most energetically favorable. It will lose the most energy there. So you would think, oh, this is the one of the three that will happen on its own, happen spontaneously. And yet, of the three, it actually won't. There's something that's hindering it. You could fill our entire classroom with methane. I would not recommend it. That would be a bad idea. But the reality is nothing would happen other than we might have trouble breathing. But nothing would happen if we filled our room with methane. Even though energetically there should be a reaction that's capable of a reaction occurring, it can lose a tremendous amount of energy. But it won't proceed without some outside push. Now, if we took a match to the room, once we did that, then we might get all roasty toasty. So that's one of the reasons we're not going to do that. And the last one there is the one that's least energetically favorable. It loses the least amount of energy, but it's also the one that occurs instantaneously and happens the fastest. And that is you mixing an acid and a base there together, and it happens to, not only does it occur quickly, in terms of almost what we would refer to instantaneously, but the reaction is done very fast. And so unlike the oxidation of the diamond, which goes very slowly, or the burning of methane, where nothing's going to happen unless you give it a little push, with the neutralization there, it happens right away. So now we're at the question, well, why is that? Why do you have one that should be the most likely to react, and yet it doesn't? It needs a little help. What is it that possibly hinders the reaction from occurring? Well, I'm glad you asked, because we're going to answer that. And the first thing is basically what we call the collision theory, which basically states that in order for any chemical reaction to occur, a collision must occur between reactant particles, and the collisions must meet two basic conditions. Okay, you have to have reactant particles have to actually come into contact with each other. Now bear in mind this happens randomly. It's not like atoms or molecules have brains and eyes and they can see each other and, hey, I want to hook up with that one over there. That atom's kind of cute. I'm going to go, hook up. Okay, they're mindless. These collisions are happening at random. So if I'm putting these two things in together, they are going to collide. But they must meet these two conditions. And if these conditions are not met, then the reaction won't occur. So this is what can possibly stand in the way of a reaction happening, even if it's energetically favorable, even if it should lose energy. These are the two things that can stand in the way. One of which is when the particles hit, they have to collide with enough force. Okay, and part of that has to do with, we talked about your reactants, one of the things they have to do is the initial bonds have to be broken. So, this is where we're getting some of that energy from. So if they hit each other, but it's not with enough force, well, okay, then it's not going to work. The other factor that has to be true is the particles must be properly aligned. This means they can't hit just any old way. There's because molecules have a certain shape, as if I'm going to bond two things together, when they strike each other, they have to meet in such a way that they can kind of link up. And if they don't link up, if you think like a train, and they have a way to connect that train, and if the one end of that train doesn't meet the other end correctly, then it's not going to link up. They can butt heads. If the side of one of the things hits the connector part to another railroad car, it's not going to work. They have to meet in just the right way, or it doesn't link up. It doesn't bond, and so there's no reaction. And so that's part of what's going on. And so we're going to look at a little bit later, we're going to look at some things are there some things we can maybe manipulate to help it collide with enough force, or help it maybe be properly aligned. And so we'll look at some factors that can affect the reaction rates and maybe speed up some of these reactions. And a lot of that has to do with manipulating these conditions. But these are some things. So I can have a reaction that is energetically favorable, but the reality is, as maybe the particles as they currently exist, they don't have enough force. And so they can hit each other all they want. Nothing's going to happen because there's not enough force there to break those initial bonds. Or maybe they're not properly aligned, and so there's nothing I can do immediately, or on its own, it's not going to react. So that's the collision theory. Now, there's another possible thing that could be, and it's kind of connected to this, that can possibly be in the way here. And just so we understand this here, what this is, okay, this little blue line that you've got drawn here, and you might want to draw it in your notes so you kind of have a visual picture. And you'll see I say reactants on one side and products on the other. Basically what this blue line here is a graph, if you want to think of it that way, of your energy in a reaction. And the first thing you do is you have to gain some energy. And we talked about this in class. You gain energy to do what? Okay, that's right, break bonds. Okay, you have to gain energy to break bonds. And so that's what you see that little hump there. So if I get my little laser pointer out here, okay, you see this little hump right here. That's the energy gained to break bonds. So you start here and you're moving up. I'm gaining energy, gaining energy, gaining energy until I reach this point. And at this point, the very top, okay, before I start to go down, my bonds are broken. And I haven't formed products yet, but I've broken my bonds. So what I started off with, my reactants, they're not really reactants anymore. I've broken those bonds. They haven't formed new bonds yet. Okay, there's something in between, and we're going to call what we name that. Okay, in just a minute here. And then I begin to lose energy as new bonds are formed. And in theory, okay, I should be losing more energy than I gain, which is why I drew it the way I drew it. Okay, now, what's the problem that can stand in the way of a reaction happening? So I go back to that question, can a reaction occur? Yes, it can. Okay, now I'm answering the question, will the reaction occur? Maybe, maybe not. Okay, one of the things that can stand in the way is what we call activation energy, and here's the definition. It's the minimum amount of kinetic energy that reactants must have before they can react. So if I'm looking at this, if I go back to my drawing here, my graph, okay, this is the amount of energy they need before they can react. I have to break those bonds first. So I have to go from here up to the top here. Once I'm at top, then the reaction is going to take care of itself. It's going to start losing energy, and it kind of becomes just a perpetuating cycle there. It's going to help itself, and it's going to continue until it reaches completion. But this is what I'm worried about, this little hump here. Okay, getting over this hump. And if my activation energy is too high, in other words, it requires too much energy to break those initial bonds, then the reality is I'm probably not going to be able to, or the reaction won't happen on its own. Okay, it will need an outside push, and a good example of that is with the methane. I can have a bunch of methane gas sit there, and yes, it's capable of reacting, and reacting quite vigorously, but it won't. The activation energy to get that started is too high to start on its own. And so it needs a little outside push, which in this case could be something as simple as a match, okay, or a lighter. And then once it gets that initial push, that extra energy from the outside, it can get over that hump and start going on its own. So that's one barrier that can stand in the way, is what we call activation energy. And that's the energy that's needed, okay, for the reactants to initially break those bonds before they react. And so make sure that you understand that and are able to explain it. Okay, the one other term that we want to throw out today before we're done is what's called activated complex. And what that is, that's an unstable group of reactants that exists for a short time between the original reactants and the final product. So if we go back with our laser pointer here, this would exist basically right at the top of this hump. Okay, once the reactants, their bonds have been broken, we've input our activation energy, those bonds have been broken, we're at the top of this hump, they're no longer the original reactants anymore. Those bonds have separated, but they're not products yet. They haven't formed anything new. So it's kind of this unstable group. They're high energy. Why? Because what have you just gotten done doing? Gaining a bunch of energy. So that's unstable. So what is it going to seek to do? It wants to become stable by doing what? Losing energy, which is the formation of products. So as they form new bonds, okay, then you get your products, and you're losing energy in the process of that. What that in-between phase is called is activated complex. Okay, and it varies from reaction to reaction what that activated complex is. And the reality is you have to kind of experiment to figure out what those possible in-between phase reactants might be. And we'll deal with that. We'll look at some examples of that at a later date. So those are some of the basic barriers that can stand in the way of a reaction happening, even if it's energetically favorable. So even if we answer yes to the question, it can occur, okay, and thermodynamics is okay, when we get to the realm of kinetics, answering that question, will it occur, sometimes we have to say no because there are some barriers that stand in the way.